Yeah.
About 10 seconds. Let us begin. Welcome back, everybody. We're going to run through a couple minutes today. Bayes Estimators, Rao-Blackwell, and then we're going to begin hypothesis testing. And that will take us into chapter 8. Just a quick comment. I won't have this video up until late tomorrow night. I have to make a run to Richmond right after class. So I agreed to do something for somebody. So apologies for that. So try to remember what I say this time. Saying that, it'll be, I'm going to guess I'm going to get home at 8 o'clock tomorrow. So probably takes 3 or 4 hours to put it all together and have it up on YouTube. If you've ever tried to upload a video to YouTube, it takes several hours. So be patient. Midterm 2 is due on Friday, and I looked at my due date on EM, and I think I said it was due on Sunday, which would have put it due on Monday, but Monday is a spring break day. So that's Wednesday. So following the rule. So hopefully you at least understand that rule, that you get to extend. I will be posting a few more book problems, probably on Friday slides, so that you can start carrying through and working through them. There's lots of problems I'll probably allude to today, too, that you can start working on. So in your infinite amount of time, you can work problems. I know that it's harder than that. There's a constraint in there. Okay. Just to remind you guys, learning inference and putting all this together, inference is this huge field. And we're covering different branches. I've spent a lot of time on estimation, but there's other things going. So this is another big thing in statistics. And we'll be talking about it a little bit more on Friday. This is the most contentious thing in all of stats. Estimation, isn't it? So it's testing, and I'll try to say why. Usually when I say the word testing, everybody freaks out a little bit, because they think they're about to get tested. So we'll test you on testing in the final exam. Big deal. So, very big deal. And you guys are going to have to deal with this in your careers as to what is the right way to test things. And the different procedures are answering wildly different questions. You have to address which question you're actually asking. So, lots to say about this. We're going to get it done in 5 lectures. So that should be enough. I do have some lectures on decision theory that I'm kind of cutting through pretty quickly in this class. So I'll probably post a couple lectures for you to watch that I filmed last year if you want more details on decision theory. So 2 hours of stuff you can watch. If you don't want to watch it, I think I've said enough. Let's just go to Bayes Estimators. So we know that a Bayes estimator, E pi, and I'll say given the data, so this is my Bayes estimator. This is my prior. This thing. And that's just the arc minimizer over the estimator itself. So this will appear in this equation of the integrated risk. So this is your loss function. It's going to depend on x right here. I've got some true parameter. Then I'm going to integrate with respect to sample. Sample depends on theta itself. I'm going to integrate over x. And then I'm going to integrate over theta. So this is risk. And this whole thing right here is average risk. So Bayesians are minimizing the average risk. So if I have some risk curve, it's a function over theta. This is a function of theta. It's also a function of the estimator itself.
I think
here in the notation. How did we weight? You might be asking lots of questions. How do you pick pi? How does Bayesian do that? It depends on the criteria you're trying to optimize to. And so it depends on which properties you want out of the posterior. I'm not prepared to go through all of that in this class, and that's why I have another class called Bayes. And it pretty much is all about how you pick pi, and then the other part is how do you compute this stuff at the end of the day. And so that's pretty important these days. We used to sweep that under the rug, and now we talk about it a lot because that's the whole point. You gotta actually compute something. So in my base class, I'll talk more about how you come up with different pi's, why you would pick various pi's. In this class, all we've alluded to is the conjugate problem, things like that. And we've said a little bit more, but not too much more. So for this class, it's sufficient to just think about conjugacy, but there's a lot more going on. So Bayesians just want to integrate over this. So they're going to look for the estimator that induces some risk. So the risk function looks like this. It's going to be a function over theta. Probably would want the risk to go down or something like that after some amount of time, you know, depending on the problem. And what the Bayesian is doing is it's just looking at this area right in here. This area is the average risk. Right here. So they're going to try to minimize that area. Some people are interested in other things, like what the maximal risk might be. And it depends, again, on the problem at hand. So if you think that doing well on average is the right criterion, you will be a Bayesian. So if you think some other criterion is the most appropriate one, you may choose some other branch. So it depends on the problem. Okay, so this looks like a hard problem. I've got to maximize, I've got to minimize something that has an integration in it. So two operations going on. That's pretty hard. Let's just reduce this to a simpler problem. So the arg minimizer over this double integral, so our loss function, theta times fx given theta. I'm going to leave myself just a little bit of room in here. So dx pi theta d theta. So here's my first step. So I'm going to drag that thing in there. So let me just do that. So that shouldn't mystify anybody. It has nothing to do with theta, what's in here. So I'll just drag my pi theta right over there. I'm going to give myself just a little bit more room. Back that thing up. So, and I'm going to divide by the margin of the data. I'm going to call that f of x. I'll tell you what that is specifically in a second, and I'm going to multiply by that. So all I've done is multiply by a funny form of 1. So f of x in all of this is just equal to the integral f of x given theta, pi theta, d theta. So I usually call this the margin. Or this is the conditional distribution of x. I marginalize out theta, and so it's on average the measure of the data, averaging over all of theta. So this thing has a different name to me, this whole block. Does that look familiar to you? What's that?
Posterior.
Posterior, yeah, exactly. So this is posterior distribution. So usually we call this pi theta given x. Then what I'm going to do is I'm going to drag this thing over here after I spin those around. So I'm not going to spend a lot of time addressing this, but this is a positive function. This is a positive function right here. It's a density function. It may be infinite support right here, but I can always spin these around because the integrand is positive in there. This is a real measure. So you'd have to take a measure theory class maybe to understand when and when you cannot apply Houdinis, but it seems like you almost always do. That's not true, but in this case you can do it. So this right here is just Houdinis. So I won't spend a lot of time justifying that I can switch the order of that integral, but if you can derive something like the iterated expectation formula and you're comfortable spinning those bounds around, you should be comfortable spinning around as well. So this is going to be equal to the R minimizer over E double integral loss function EX theta posterior distribution d theta fx dx. So I want to just point out what we're doing with this arc minimizer here. It's only operating on this interior integral. There's no e's anywhere else. So for any given data set that I have in the first place, because this is the whole of conditional analysis right here, where I'm conditioning on x. So conditional on an x that I observe, all I have to do is optimize this thing right here. Doesn't have anything to do with that. That's the nice point right here. So this is going to give me the same solution as the arc minimizer over the interior integral. And I don't need to average over x. Again, just because E doesn't appear here. So this is going to be the loss function theta integrated over the posterior distribution d theta. And so that's also what Bayesians are optimizing. And so it seems like an easier problem because I've removed an integral. And then I recognized it as a problem that I kind of know how to interpret. So this right here is the expected posterior loss. And I kind of like this a lot because it's a conditional analysis. It's given the data set, what do I think the estimator is? And I kind of like talking that way. So I like thinking, given my data set, what do I think my estimator should be? And that's what this says to me. So it's not just an optimization problem, but it's a procedure. So the procedure for getting an estimate, or an estimator. Let's look at an example. Bree asked me this 2 minutes before class. How do I know that the mean is the optimal thing? And we're almost there. We just need to plug in the L2 loss function if we want to talk about the mean. Let's do it. So for L2, or mean squared error, however you want to describe this, just an example. We're going to have E pi is going to be equal to the integral, the arc minimizer. Give myself some more room. The arc minimizer over E integral, and I just plug in my L2 loss function right here. So this is going to be E. And I'm just going to shorthand this, just write down what E is. So I'm just going to call magnification ever so slightly, I know E is going to depend on the data. Squared posterior distribution. D theta. This is not a hard problem. How do I find this? What would you do? If I make this L1, it's hard. What do I do for this function to optimize it? Or to minimize that thing?
Just take a derivative.
Yeah, take a derivative. So smooth function, so let's take a derivative. So what we're just going to do is we're going to dE integral, give myself just a little bit of room here, E minus theta squared, posterior distribution, D theta. So I can slide that right in. No problem. Everything is positive. So I can switch the order. Derivatives and integrals can be switched if integrals and integrals can be switched. It's like switching adds and subtracts. They're the anti-properties of each other. So Houdini holds for integration, it holds for derivatives as well. And mixtures between the two things, because they're really the same operations in reverse. And so this is just going to be equal to 2 integral E minus theta posterior distribution given x d theta. So here's my big step where we pick on you if you do this step wrong. But as soon as I set this equal to 0, I've defined the procedure. I'm minimizing this, I'm optimizing it. And so I need to be specific in my notation. So that gives us integral 2 E minus theta posterior distribution given x d theta is equal to 0. And as soon as I do that, I better put my hat right there to tell you that it's not true E anymore, it's my estimate. So, and then I solve for everything. You'll notice this 2 doesn't matter. Right here, it cancels. And when we rearrange everything, we wind up with our solution.
What's the tool that it was L1 dot?
We're not done with this problem yet, Marie. So let's finish it. You're asking about L1?
Yeah, what's the tool because
Hold on. Let's finish. So this is just going to be integral theta d theta is equal to integral E pi theta given x d theta. E has nothing to do with theta. E had something to do with theta. It's not an estimator.
It's an E hat, right? It's an E hat. Sorry, it's an E hat.
you have
E hat. Yes. Yes. I pick on you, you pick on me. I can pull that thing out, and I know how to do this integral. What's this?
One.
Integrating over some distribution right here. So E hat is equal to this thing. And that's the posterior. So this is expectation theta given x. And all of these sort of quadratic functions work out the same. If you're optimizing something under some sort of quadratic norm, you're always going to get the average back, just in the context of the problem. So if you're integrating with respect to the sampling distribution, then the answer would be the distributional mean. If you're optimizing with respect to a sample itself, then you're going to get the sample mean. If you're doing this with respect to a posterior distribution, you're going to get the posterior. They're all the same problems in these guys. So Marie wants to know more. She wants to know what about L1. So L1's a little bit harder. So for L1, I'm not going to do it here, but you can't do calculus. So I'll just refer you to a problem in the book. See problem 7.13. So I think what they do is they say optimize lambda e to the minus lambda x minus e, something like this. Anybody recognize this distribution? There's a half in here. X can be anything between negative infinity and infinity. We'll just put in some parameter right here. Let's make it bigger. You might want to optimize this if I have xi's coming out of this distribution. It's not the same problem is our problem for the posterior distribution, but it is the same problem. So I'm optimizing something under the absolute norm. And it turns out to be the exact same strategy you would use to estimate, find the estimator under the L1 norm in a Bayesian context. It is the same problem. So why do I say it's the same problem? E is a monotonic function, and so maybe maximizing this thing is equivalent to minimizing something with respect to the absolute norm. They'll walk you through that in problem 713 in Casella and Berger, so I encourage you to look at that problem. The nice thing is that solution is floating around as well. So your solution manual will have that. If you didn't know there's a solution manual, Casella and Berger, kudos to you. So it's floating around there. So you look at that and walk through it, and they'll take you through it. They'll basically partition the space into two things, and they'll show you what's going on in those two parts of the cell. Any questions about that? So Bayes gives you this nice procedure that's conditional on the data. And it turns out there's lots of nice properties of Bayes estimators. I'll upload a couple videos for you, or at least I'll post them to the Slack page if you want to watch them over the summer or something like that. And I'll go through more of this in my Bayes class. You guys want to join for that. Shameless plug, right? Still a good one. Okay. Moving on. Rao-Blackwellization. This isn't too difficult. Erase it. I will point out many Bayesians converted based off of this optimization problem. Thought it had nice properties. And so usually the aesthetic isn't the thing that sells people, it's the properties of the analysis and how useful it is. So I've seen a lot of people tell me they became Bayesians when they did decision theory, not through kind of just the likelihood times prior. It makes sense, it's a little bit argument. So studying the decision theory behind this and the property of certain estimators, you might like it. Okay, Rao-Blackwell. So they say, consider, so I'll just say, consider a problem. So this is just arbitrary, where I have some data coming from some distribution, and it contains some problem, some parameter data. So typical stuff. This doesn't have to be IID. So I'll just write it down like this. Kappa X comes from some distribution. So you can think of this as a vector of data. And it doesn't need to come from an island distribution. This is always going to be true. So consider an estimator. W. Why did I pick W? Because the book picks W for all of this. And a sufficient staff. T. Why did I pick T? Because the book picks T. So, and we're going to let the estimator have this property. So where expectation of W is going to be equal to, let's see what the notation is for these. I think I remember. How theta. They like how in the book. Come to me, I can now see it. So they say W is an unbiased estimator of how theta. It might be biased for theta, so it's some function of theta. Okay, so say you're trying to estimate some theta. So they made this a little bit general, but if you were trying to estimate theta, you could like out your identity function. We haven't said anything about how we constructed W. So maybe I've got some weird method, I get W. It's got some property that the expectation is equal to some function of theta, and I'm pretty happy with that. And if I wanted to know what theta was, maybe I unwind tau, take the inverse function, something like that, and get theta. So we've seen a lot of estimators in this class that are good, and we've seen estimators that are not so good. And so possibly W could be improved upon. And Rao-Blackwell gives us a methodology for always guaranteeing to do it at least as good as you've done already and maybe better. This is what Rao-Blackwell said. This is called Rao-Blackwellization. So to Rao-Blackwellize your estimator, we're going to consider a function of T, the sufficient stack. And we're going to build our estimator like this. We're going to take the expectation of W, and we're going to condition on the sufficient stack. So this is the Rao-Blackwellized estimator. The Rao-Blackwellized estimator. So they say take your estimator, condition on the sufficient stack, and take the expectation. And they showed that both these things are true. The expectation of our Rao-Blackwellized estimator is equal to tau theta. So we get back the same thing in terms of expectation. So we don't change the point property of the estimator. But we are going to reduce the variance. The variance is going to be smaller than the variance of W. And that's always going to be true. It could be equal to each other. So they're equal to each other. It means you've already probably used the sufficient stat. Probably. Let's prove this. So Rao-Blackwell gives us a procedure for not changing the bias of the estimator, but reducing the variance. So that's kind of a nice thing. Now I will point out, maybe I could take the Rao-Blackwellized estimator condition on the sufficient stat again, and maybe you reduce the variance even further. You cannot do that. Once you've done it once, you can't keep repeating the process. I can't condition on the sufficient stat again. You'll get exactly the same answer back. You can verify that for yourself. But here's our proof. And I love easy proofs. I've said that many times this might be the easiest proof in the class. This isn't. This is definitely the easiest one. So let's just look at the expectation of BT. Let's just say this. Expectation of BT. To replace its name. Expectation of the expectation of BT. This is going to be expectation of W given B. I should say. So we've just replaced the name of BT. It's that procedure, an expectation. And I learned something once upon a time, that this thing is the expectation of W. So the double expectation of something is the expectation of that first thing. So I should probably tell you what all these expectations are over. This is W given T. What's this one over?
Or T?
T. So we'll be a little bit more polite than some people and tell you what we're taking the expectations over. And you can prove this formula using Fubini's as well. I think we've done that before. So this is equal to tau theta. So check. They're correct. Did not change the level of bias. So whatever level of bias you have for theta or whatnot, this procedure will preserve it. So if it's an unbiased estimator of theta itself, you will have an unbiased estimator of theta at the end of the day after you Rao-Blackwellize. So if I were trying to estimate theta itself, and I took tau inverse over here and I got some function of theta, that might be a biased estimator for theta. You have that same level of bias over here. Nothing changes. Let's write this down. Next part. So variance, we'll start with W. And we'll use the iterated variance formula. So this is going to be the expectation. Let's do that one second. Let's do the variance of the expectation of W given T. I've decided to condition on T plus the expectation of the variance W given T. This thing is always positive. So I know that this whole thing is greater or equal to the variance of the expectation of WT. W given T. And this, of course, is the variance of our Rao-Blackwellized estimator. So we're done. So we'll tell you this. Conditioning on something provides information. And information reduces variability. So regardless of what I conditioned on, I'm always going to reduce variance or keep the same level of things. If I put things that are independent of W in there, then I don't help myself at all. I have the same variance level. But if I provide information and I condition on it, it drives down variance. I kind of like that. Yes?
What's the sufficient statistic work?
Yeah, it wasn't in there.
Yeah.
So that's the whole point, is that I never use sufficiency in here. This is true regardless of what I do. So I can replace all my keys with smiley faces, anything. And it's still true. So conditioning on something doesn't change the bias level. That was true up here as well. So there's nothing specific about it being a sufficient stat. So that begs the question, why does T need to be sufficient? Does anybody know the answer?
Does that have something to do with Basu's theorem or something like that?
Say it again.
Does it have something to do with Basu's theorem? I might be totally off there, but there's something special about it. That
So Basu's theorem says something about a relationship between sufficient stats and ancillary stats.
yeah, yeah.
So not Basu's theorem. Think about what sufficient stats do. So think about this distribution right here. W given T. Right here. If I happen to plug in the parameter right here, being sufficient means it has nothing to do with the parameter. So that's a property of sufficiency. That means that this thing right here is not a function of theta. And so if this was a function of theta, it's not an estimator. So if I ever ask you to estimate something and you need theta to do it, that is my biggest pet peeve in this class. Somebody will do this on the final exam. Don't let it be you. So if you write down something for your estimator that contains the true parameter, just use the true parameter. So that's not an estimator. You're out of a job. You know, you need the truth to use what I'm going to tell you. I'm not going to give you the truth back. I'll give you something else. It's not a very good analysis. So by conditioning on a sufficient stat, you're guaranteed to have something not a function of the parameter. Let's look at an example. I think this is in your book. I'll have you do the kind of reverse example by yourself. I might ask you how to do this on a final exam. So, example. So, this is a bit contrived, but just to highlight the point that we're making here. So consider x1 is coming from a normal distribution. I'll say with parameter theta, variance 1, just to make it easy. And x2 also comes from a normal distribution. So these are IID replicates. Two draws from the same distribution. So goal, estimate theta. So here's one such estimator. X bar expectation of x bar is equal to theta. This is just going to be x1 plus x2 divided by 2. Let's try to Rao-Blackwellize this thing. Now, you might already know that x bar is the min sufficient statistic. And so if I try to condition on x bar again, it's just going to give me x bar back. If I try to condition on the sum of the xi's, there's no extra information. it'll just give me X bar. So if I try to Rao-Blackwellize that estimator, it won't change anything. Try to convince yourself that that's true. You can do it formally. So I'm saying it rather intuitively. But let's not Rao-Blackwellize. So not Rao. This is not a Rao-Blackwellization. Something different. So let's just come up with this thing right here. I'm going to make it a function of something that's not a sufficient statistic. This is not sufficient. I'll say this is expectation of our old estimator conditional on x1. Let's see what happens right here. So this is not Rao-Blackwellization. That is not a sufficient statistic. It'll still be true that I'm able to reduce variance. Possibly. I'm not going to make it any worse, conditioning on something never messes you up. Got to condition on the right stuff. That's what stats is all about. That's what model building is all about. So this is just expectation of x1 plus x2 divided by 2, conditional on x1, which is 1/2 expectation of x1, conditional on x1, plus 1/2 expectation of x2, conditional on x1. We know what that is. It's x1. So 1/2 x1, everything feels pretty good. And here's where we lose out. These are IID, so that conditioning isn't doing anything for us. What's that? That's theta. So oops, I built something that doesn't help me. So not an estimator. That's why we condition on sufficient stats, so we don't do something like that. So certainly this thing has less variability than this thing right here. But I don't know theta, so I can't use it. The only thing fluttering in here is that right here, instead of both of them fluttering. But it doesn't help me because I can't use it. So that's the answer to that question. Let's think about the other way around. Here's an example with Rao-Blackwellization. And I'll let you work through this because good practice. So same exact setup. So consider our estimator W is equal to x1. So let's say I use something that's not sufficient. Not sufficient. But I happen to know that some of the xi's or x bar, it doesn't matter which one you condition on, you will get exactly the same answer. So x bar is sufficient. So Rao-Blackwellization says to do this. So if somebody gave me this right here, and I knew that, well, x1 is unbiased, but I can do better. So I can reduce the variance. We could look at expectation of x1 given x bar. And that's our Rao-Blackwellized estimator. So the question is what is this thing? You guys have any idea? Here's how you work through it. To figure this out, what you do, step 1 is write down the joint distribution for x1 in X bar. So when I'm trying to figure out what conditional distributions are, I first start with the joint, and then I build the conditional out of it. So this thing right here is normally distributed. They both have the same means, theta and theta. And they have some covariance structure. So the variance for x1 is 1. What's the variance for x bar?
1 over 2.
2. What's this? We need to figure it out. So these things are covariances. This is the covariance of x1 with x1 plus x2 over 2. Just do this very easy problem. So this is going to be the covariance of x1 with x1. I'll take my 1/2 out in front, plus the covariance of x1 with x2. I can drag my 1/2 out in front there as well. Basically, whatever these are producted into, just take those as a product out. So these are independent, so that's 0. And this is 1. That's really just the variance of x1. So how does x1 vary with x1? That's what's the variance of x1. So these are a half. Right here. Then figure out what the joint distribution is. So step 2, find x1 given x bar's distribution. You should be able to pop these out off the top of your head. So it's going to be a normal distribution, and it will have the conditional mean and the conditional variance. If you've taken a regression class anytime lately, you should know those formulas, or be able to derive them very, very quickly. And so I'll let you do that, and I'll probably ask you in the near future what the answer is. Anybody have a guess? It's x bar. It'll give me x bar back. And if I conditioned on some of the xi's, I would get x bar back as well. So work through that. So it's good exercise. It'll take you through your conditional normal theory, which is the underlying theory for regression. So this is a regression. x1 on x bar. This is the way I look at that. Conditional distributions are regression problems. Maybe you think about it that way. Let's move on. Hypothesis testing. So this one is a big can of worms that we're about to open up. So testing. Hypothesis testing. The whole goal of this is to select out of 2 or more competing hypotheses. Which is most compelling. Now the book doesn't say this. The book says, so this is me, says me. And the book says is true. This is the book. We'll never know the truth. That's the problem I have with this. You won't know the truth. The only thing that's true is that even if you knew the truth, you wouldn't really know if you knew it. Chew on that for a little bit. Let me just ask you a question and we'll conclude, and we'll come back next time. we'll start looking at the tools that we use to decide between hypotheses. There's a whole bunch of them, and sometimes they come up with similar answers, and in some cases, you get wildly different answers. But I'm just going to leave you with these two questions. Can you ever know what is the truth? My second question is, can you ever know what is false? What's the answer to these questions? So, I think I answered this. You can't know. What about this one?
I think you can know.
Maybe. So it's at least an easier problem. And so possibly I could have some hypothesis about gravity, and I say, well, gravity pushes objects apart from each other. And then I go to test it, and I find out that doesn't happen. So I'm able to falsify it. So this is an easier question. So all we can do is falsify. The hypothesis. We can find contradictions. We can assume things are true, and then we can see that things lead to a contradiction. Now, in statistics, we don't see a mathematical contradiction. We see evidence that leans against the hypothesis. That's not the exact same thing as falsify, but it's at least in the ballpark of it. This is all attributed to Karl Popper. So basically, they give us the whole idea of the scientific hypothesis in the first place. So for something to be scientific, for something to be theoretical, we have to have the ability to test against it. That's what we're always arguing about. So if it's science, we have the ability to test against it. If we don't have the ability to test against and the ability to falsify something, we don't call that science. That's just all there is to it. And so statistics are a little bit harder because we don't actually get to falsify exactly. We get in the ballpark of that. And that creates lots of controversy as to what is the level of evidence that we use to falsify something. And that's unclear. So we're going to talk about that point. But I will just say, Bayesians are looking at things very relatively in terms of distances, and Neyman-Pearsonians, which are frequentists, look at things very absolutely. And really we're arguing about relative distances versus absolute distances. And I'll try to make that point in the next 5 lectures. So that's it for now, you guys. Be patient on this lecture coming up. I'll have it up tomorrow evening at some point, probably a little bit late, and I'll see you Friday morning. Good luck.